Lab 3, Circuits. Purpose. The purpose of this lab was to predict the behavior of circuits using a multimeter to measure the currents and voltages at different points in the circuit. Procedural overview. First, we created this circuit. It has two batteries in series at 1.5 volts each with two multimeters and two resistors. We read the values at I1 and I2. The value at I1 was 18.9 milliamps. I2 was 19.1 milliamps. The values should theoretically be the same, but due to the accuracies of the multimeter, they are slightly different. Then we converted one of the multimeters to read the voltage. The voltmeter read 3 volts, which makes sense because the EMF source was two 1.5 batteries in series, so the total voltage is the sum of the two batteries. Then we read the voltage drops across the different elements. So across the battery was a positive 2.9 volts. The voltage drop across the 47 ohm resistor was 0.9 volts, and across the 100 ohm resistor was 1.9 volts. And so if we do 2.9 subtract 0.9 minus the other 1.9 volts, it's not actually 0, but it's pretty close. It's 0.1 volts. And when the voltmeter is attached to the circuit, it acts as a load in parallel with a very low resistance. And so for the calculation of the resistance for the 47 ohm resistor, resistance is going to equal the voltage divided by the current. So the average of the two currents was 19 milliamps. So we did 0.9 volts divided by 19 milliamps. And that gives us a resistance of 47.368 ohms, which is very close to the 47 ohm resistor. And we did the same thing for the 100 ohm resistor, and we got the value of 100 ohms. And the resistance across the wires, the multimeters, and the batteries is very small and was not accounted for. For the second part of the procedure, we created this circuit, which was just a simple RC circuit of the batteries, a capacitor, and then a light bulb. We measured the brightness of the bulb to basically tell how much or how fast the capacitor was being charged and discharged. So when we have the batteries hooked up, the bulb brightness was pretty immediate. And then once we removed the battery to where it was just the capacitor and the light bulb in series, the light bulb stayed illuminated for about 12.9 seconds before it stopped glowing. This is pictures of the lab setup. Some of the fundamental physical principles is Ohm's law. So the current equals voltage divided by resistance. Current is just a charge at a place over a certain amount of time. The capacitance equations where capacitance equals the charge divided by the voltage, and then Kirchhoff's voltage and current laws, which say that the sum of voltages in a loop is 0, and the incoming currents at a node is equal to the currents leaving the node. So the sources of error, one of them was negating the resistance of the batteries and the wire leads. They are very close to 0, but not actually 0. And then the accuracy of the multimeters. Most multimeters usually have an accuracy of plus or minus 1% of whatever's being read. So what if? So what if we charge the capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Will this prediction happen in real life? Explain, blah, blah, blah. Okay, so the time it takes for a capacitor to reach full charge, which is about 99% of the supply voltage, is 5 time periods, where the time period is defined as the resistance of the circuit multiplied by the capacitance of the capacitor. So the time it takes would be 5 time periods. If the resistor is removed, the R value goes to 0, and so does the T value. So the time would theoretically be 0 seconds, or instantly. But the charging is not 0 seconds. It's approximately 1 second, so very fast, but not instant. This is because there is some resistance in the battery and the wire themselves. It is very small, but it is not 0, and and therefore the time it takes to charge is not zero. So in conclusion, the circuit responded in a way that is described by Ohm's law and Kirchhoff's voltage and current laws and the laws of capacitance.